Hello everyone, this is Krishnasri and my registration number is 22B01A0555. I and Anushka are going to present this presentation on deadlock avoidance bankers algorithm. Let us see what is meant by a deadlock. A set of processes are said to be in deadlock if every process is holding some resources and is waiting for additional resources but which are acquired by another process. A deadlock happens in operating system when two or more processes need some resource to complete their execution that is held by other process. A deadlock may occur if the four Kaufman conditions hold true. So the necessary conditions for deadlock in operating system are mutual exclusion, hold and wait, no preemption, and circular wait. If these four conditions occur simultaneously in a system, then we can say that there is a chance of getting deadlock, but it is not guaranteed that a deadlock is encountered. Coming to mutual exclusion means a resource can be shared by only one process. To avoid deadlock, we need to overcome mutual exclusion. That is, to share a resource among multiple processes simultaneously, which is practically impossible. Next come to hold and wait. A process is holding some resource and is waiting for additional resources which are acquired by some other processes. No preemption. Preemption means a process cannot release its allocated resource until its execution completion. Example printer. No preemption means process should stop its execution in the middle and hand over it to other processes to avoid deadlock, which is also not possible for certain type of resources like printer. Circular wait. A set of processes waiting for each other in a circular form are said to be in circular wait. If these four conditions hold true, we may say that a deadlock may occur. Let us consider an example to check the occurrence of a deadlock in an operating system. In this example, process 1 is holding resource 1 and waiting for resource 2, which is acquired by process 2, and process 2 is waiting for resource 1, which is acquired by process 1. So there is a circular wait among the processes for the resources. So there is a chance of deadlock here. So for smooth running of the system, we need to find ways to avoid deadlock. There are two ways in which we can avoid deadlock. That is by using a resource allocation graph and by using Banker's algorithm. Generally, resource allocation graph algorithm is used when a single instance of resource type is connected to computer. And Banker's algorithm is used when multiple instances of resource type are connected to computer. The Banker's algorithm is used in operating systems to avoid deadlocks by managing the allocation of resources to processes. It ensures that resources are allocated safely by checking if granting a resource request will lead to a safe state or not. The Banker's algorithm is named so because in this algorithm is used in banking systems to determine whether a loan can be granted to a person or not. Let us see the characteristics of Banker's algorithm. If any process requests for a resource, then it has to wait. This algorithm consists of advanced features for maximum resource allocation. There are limited resources in the system we have. In this algorithm, if any process gets all the needed resources, then it is that it should return the resources in a restricted period. Since Banker's algorithm is for multiple instances of resource type in a system, various resources are maintained in this algorithm that can fulfill the needs of at least one client. There are two types of Banker's algorithms. One is safety algorithm and the other one is resource request algorithm. Let us see what is meant by safety algorithm. A safety algorithm is an algorithm which is used to find whether a system is in its safe state or unsafe state. Resource request algorithm. A resource request algorithm is mainly used to determine whether request can be safely granted or not. That is, before granting a request, that is, before granting a resource to the requesting process, the system checks whether the system will be in safe state if it grants that particular resource to that particular process. Certain data structures are required for implementing Banker's algorithm in an operating system. Available. It is a 1D array of size m indicating the number of available resources of each type. Available of jth index equals to k means there are k instances of resource type Rj. Max. It is a 2D array of n into m size that defines the maximum demand of each process in a system. Max of I, jth index equals to k means process Pi may request at most k instances of resource type Rj. Allocation. It is a 2D array of size n into m that defines the number of resources of each type currently allocated to each process. Allocation of I, jth index equals to k means process Pi is currently allocated k instances of resource type Rj. Need. It is a 2D array of size n into m that indicates the remaining resource need of each process. Need of I, jth index equals to k means process Pi currently needs k instances of resource type Rj. Need of I, jth index equals to max of I, jth index minus allocation of I, jth index. Now let us take a look at Banker's safety algorithm. Let work and finish be vectors of length m and n respectively, where m defines the number of available resources and n is the number of processes waiting for the resources. Now initialize work equals to available, and since all the processes initially do not complete their execution, all of them have a false value in finish array because uh, resources are yet to be allocated for their execution. So in the next step, we need to find an I such that we need to find a process such that it did not finish its execution and its need is less than the available resources. Then if there does not exist such a process, then we need to go to the fourth step, which tells that all the processes have completed their execution and the system is in safe state. If at all all the processes did not complete their execution, then we need to go to third step. In third step, in third step, we allocate the required resources to the process and make it get executed completely. And then we add all the resources acquired by that process to the available resources and mark it as completed. So we can mark that the process execution is completed, and we again go to the second step and check whether if there is a process whose execution completion is yet to be completed, and again we follow the same process until we reach the fourth step where all the processes have completed their execution and the system is in a safe state. Now let us see an example for banker safety algorithm in which there are three types of resources A, B and C. A has 10 instances of its type and B has 5 instances of its type and C has 7 instances of its type. In this example, there are 5 processes, namely P0, P1, P2, P3 and P4, whose maximum need as well as allocated resources are given in a tabular format. As we see, uh, we need to calculate available resources at a particular instance when a particular process needs to be executed every time, and also their need after getting allocated some resources initially. First, let us look at the number of available resources after some resources are allocated to some processes. First, let us take a look at resource type A. We can see that two instances of resource type A are allocated to process P1, three instances of resource type A are allocated to P2, and two instances of process resource type A is allocated to process P3. So in a total of seven instances of resource type A are allocated to processes. So as we know that there are a total of 10 instances of resource type A, 7 are allocated to the processes initially. So there are only 3 available resources at present. As we see for the resource type B, its instances are allocated, a single instance of resource type B is allocated to process P0, and a single instance of process of resource type B is allocated to process P3. So a total of two instances of resource type B are allocated to the processes initially. So since five instances of resource type B are available in the system and two are already allocated to the processes, there are only three available instances of resource type B. As we look at the instance type C, there are two instances of resource type C allocated to process P2, and one instance of resource type C is allocated to process P3, and two instances of resource type C is allocated to process P4. So a total of five instances are allocated to processes initially. So as we know that seven resource instances of resource type C are initially available, out of which five are initially allocated to the processes. So we have only two available resources now. Now let us check for the allocation of resources for the process P0. As we see, the maximum need of process B0 is 7 instances of resource type A, 5 instances of resource type B, and 3 instances of resource type C. We can see from the allocation table that an instance of resource B is already been allocated to process P0. So it still requires 7 instances of resource type B A, and 4 instances of resource type B, and 3 instances of resource type C. But the available instances are of resource type A is 3, and resource type B is 3, and resource type C is 2. So it is not possible to allocate them to the process P0. So we'll leave process P0 and next go to the process P1. Uh, Here we can see that the process P1 needs three instances of resource A and two instances of resource B and two instances of resource C to complete its execution. Already, two instances of resource A is being allocated to process P1, so its requirement is only one instance of resource type A and two instances of resource type B and two instances of resource type C, which is less than the available resources. So we can happily allocate them to the process P1 and make its execution get completed. After completing its execution, all the allocated resources are added to the available resources. So the allocated resource instances of resource type A, which is 2, is added to the available resources, which then becomes the available resources become the instances of resource type A available become 5, the instances of resource type B which are available becomes 3, and the instances of resource type C which are available become 2. Now let us move forward to look into the need of process P2 for its execution completion. So the process P2 requires 9 instances of A and 0 instances of resource type B and 2 instances of resource type C. But the available resources of instance type A, resource type A is only 5. So we cannot allocate resources to process P0, P2. So we skip that process and move further. On moving further, we see that process P3 requires two instances of all the resource types to complete its execution. Since the available resources are greater than and equal to its equal requirement, we allocate the resources and make the process P3 to complete its execution. Upon completing its execution, we take away all the resources and add them to the available resources. So the available resources would become 7, 4, and 3 of the respective resource types. So like next we'll move to the process P4, where we see that the maximum requirement is 4 instances of resource type A, 3 instances of resource type B, and 3 instances of resource type C. And the already available resources are 7 instances of resource type A and 4 instances of resource type B and 5 instances of resource type C. And we also see that 2 instances of resource type C are already been allocated to process P4 initially. So the requirement is only 4 instances of resource type A, 3 instances of resource type B, and 1 instance of resource type C, which is less than the available number of resources. So we can happily allocate them to the process P4 and get its execution completed. Then we can add the allocated resources to the available resources. So we get 7 instances of resource type A, 4 instances of resource type B, and 5 instances of resource type C for readily available for another process execution. Now since we have completed one round of all the processes, we again go to the top to check if there is any process whose completion is yet to be completed. We find that P0 process is not completed execution. So we check if the available processes are greater than or equals to its need. Since we already knew that 7 resources are needed for resource type A to complete a process P0 execution. Now, after completing all the other possible process execution, we get 7 instances of resource type A available. So, 7 instances of resource type A are available for the need of process P0. And also, since the process P0 requires 4 instances of resource type B, now we have 5 instances of a resource type B available. So we can allocate process resource type B also. If we check for process P not's request for resource type C, it needs 3 and 5 are available. So we can happily allocate all the available resources to the process P naught and get its execution completed. Upon completion of process P naught execution, we can check for any other process whose execution is yet to be completed. Then as we see, we can find process P2 whose execution is yet to be completed. As we know, its need is 6 instances of resource type A and 0 instances of resource type B and 0 instances of resource type C. Since all the available resources are greater than the need, we can happily allocate them and get process execution completed. Upon completion of execution, we add the allocated resources to the available resources. After all the processes execution completed, the available resource is equal to the number of instances of resource type which are present in the which are connected to the system. So this is about a safety banker safety algorithm. Now let us have a look of the other type of banker's algorithm, that is resource request algorithm. It is also similar to banker safety algorithm. Now let us see the algorithm of resource request algorithm. If request of a process is less than its need, we need to go to second step. Otherwise, we should raise an error condition since the process has exceeded its maximum claim. If in the when we go to second step, if request of a process is less than or equals to available resources, then we need to go to third step. Otherwise, the process must wait since the resources are not available, and it should wait until all the available required resources can be obtained for its execution. In the third step, we have the system pretend to have allocated the requested resources to the process PI by modifying the state as follows. Available equals to available minus request. Allocation equals to allocation plus request. And need equals to need minus request. Now let us consider an example for resource request algorithm in which resource types A, B, C are present and 10 instances of resource type A is present and 5 instances of resource type B is present and 7 instances of resource type C is present. As we can see that the only difference between resource request algorithm and banker's safety algorithm is that in resource request algorithm, a particular process will raise a request for the allocation of resources to complete its execution. In banker's safety algorithm, there is no particular process which raises a request for allocation of resources. We go in a manner in which OS is defined to do, and we do not follow a particular order. OS takes care about the order in say, banker safety algorithm according to some particular schedulers. But in resource request algorithm, at the very first instant, the process raises a request for the allocation of resources, and then the OS then follows the same way as it does for Mango safety algorithm. In this particular example, process P1 raises the request first, so the OS checks for the allocation of resources whether it would create a deadlock situation if process resources are allocated to the process P1, and it allocates based on that or deallocates. Then from the very next step, it follows the banker safety algorithm.